Welcome to ENVS254, Introduction to Remote Sensing. I'm your instructor, Karina Butterworth, and I will be taking you through this journey of remote sensing throughout this semester. So these videos, just as a quick introduction to these videos are being posted kind of intermittently, but they are there for you to access, and you can come here and watch them anytime, review the material. They were more specifically focused on the course outline instead of the in-class component, which you would see as more activities and dialogue and everything else. So without too much description, I'm going to jump right into our first module. And the first module outcome is define the principles and various components of remote sensing. So to break this down, I take the course outline, I am introducing the outcome, so I look at module 1, and then I'm going to break it down into individual objectives. So for those of you who've been following my channel here, this is going to seem very repetitive, but sometimes the ways things are described differently in different videos may be helpful to you. So our first objective in this course is define remote sensing. So I did a little word cloud here with remote sensing because usually I like to pull from you what you really think remote sensing is. And some of the more common words, I've put them here in this word cloud, but there is an actual formal definition of remote sensing. And if you are listening to this, that's how you're going to get it. And so my definition of remote sensing is that it is the art, technology, and science of observing, measuring, analyzing, and synthesizing data from a distance that with respect to a target or with respect to a feature. Now, remote sensing doesn't necessarily have to be just like from space or just from airborne, like on an airplane. You can also think of remote sensing as taking a photograph from your own camera. Remote sensing such as our eyes that are observing the world on a daily basis. You can also think of remote sensing in terms of medical imaging as well. So that's another aspect of it. So you can see here that I've kind of taken all those concepts and just put the words in here. So you can see the words light, so that a lot of people consider light as part of remote sensing. We'll get more into detail about what that really means later. Then engineering, technology, measurement, maps. A lot of people like to make maps as a final product from remote sensing. Object, which is what we're looking at. Distance, and so we're looking at a distance away from something else. Satellite, contact. So contact would be no contact, right? So we wouldn't have any contact. Airplane, synthesis, science, target. So targets can be something that you've actually put on the ground. They can be something that you've identified and you know what the coordinates are. And it can also be something that is just what you're trying to take a picture of, right? So it can be mean a lot of different things. Image, pixel, because again, image is what you get in the end. I'm not going to refer to them as pictures because to me, a picture is something that you hang on your wall. An image is a workable object. So again, there may be other definitions of that as well that come up through other people that you talk to, but I work with images because I feel that I am able to manipulate them, and that's what I do in remote sensing, where a picture is kind of a static object to me. And we have pixels, which are parts of the images, and we'll get into that a little bit more later. Observations, cameras, features, and analysis. So remote sensing takes in a lot of different things. And the biggest part about remote sensing is, especially in environmental technologies like what you guys are working on, remote sensing is covering any aspect of the environment that you can imagine, right? So maybe we can't sample water with remote sensing, but we can detect different elements within water from a distance, because it might change the thermal signature, it might change the water quality, it might change maybe even it might make it less transparent and make it more opaque, right? So with remote sensing, we can detect those types of things. And it's not always stuff that we can see with our eyes, which is always kind of a cool thing to talk about. So that's remote sensing, kind of an introduction to what it is. So moving into the next objective is 1.2, and that is defining the concept of a remote sensing system. Now, this particular objective in the course outline, I'm not a big fan of how that's written because a remote sensing system can mean a lot. So I'm going to take kind of two perspectives on it, and we'll talk about why I went that way. So let's go with this particular remote sensing system. So a system needs to have a source of energy. It needs to have a receiving part for that energy. It needs to have a medium to transfer through, and it needs to have something to interact with. So we can see in this particular citation here, this resource, they have the sun as a energy source. They have a satellite and sensors as the platform. Satellite is a platform, and sensors is the receiving information of all this energy. So the sun sends radiation from itself, and now radiation is not always a bad thing. Like even basic light can be considered radiation. It travels through the atmosphere and interacts with different targets. And every target or object or feature on the ground shows to be, has like a different kind of reflection. So if you think about it in terms of light, we can deal with color. And so this one would show gray, this one would have a red part to it. Roads would be gray as well. Vegetation might be green, water blue, etc. So it travels through, it interacts with that target, and then it scatters back to the sensor, or not back to, but to the sensor. So there's three words here that they've used in this diagram. So the first one is emission. So let's say I'm looking at long wave radiation, which would be thermal energy, which we'll be getting into later in the semester. So emission is when the object itself sends out its own energy. So you can also think of it like as heat, right? So our bodies create heat and it sends it out. So if we take a thermal image of our body, we're going to see heat. The same happens when you have a light bulb, right? Like, so if I turn on a light bulb, it is sending energy to my sensor, and my sensor is going to receive that. So you think about that as, look, these windows have lights on, and therefore it's emitting energy to my sensor. The next one is reflection. So reflection, we consider that a pure type of interaction with the target. So we have our energy, it comes down, it hits that at a very particular angle, which is known as the incidence angle, and then it reflects as the reflection angle. The incidence angle is equal to the reflection angle, and that is reflection. So very specific to that. So for example, if you have very smooth water, you'll often have sunlight just go reflect right off of it, right? So that would be considered reflection. Then we have scattering, and scattering means it is really what happens to like everything else in the world. So the light comes down, it hits an object, and some of the light comes back to the sensor, some of it goes away, some of it goes through, some of it's bouncing around still. So you hit the tree, for example, here, and you can see that the light rays are much smaller as it goes back, even though I guess reflection doesn't do that, but doesn't show any difference. But the scattering, it hits and it's going to have arrows going in all directions, even back to the sun. So scattering means it goes every direction. Reflection means it only goes one direction. So that is the kind of the interactions through the whole system. Then it comes to the sensor. The sensor gathers that data in cells or pixels, and then it sends through telecommunications to an Earth station, and then they upload it to a web page. So in our class, we're going to be using Earth Explorer and we're going to be using Landsat data to look at. But for any, you can always use MODIS or whatever type of, even a airborne system or your own camera from your own phone when talking about remote sensing, and that makes it more relatable, right? So that's really the whole system in a nutshell. So if I go to the next slide here and just kind of bring in some of those words that I was talking about. So again, some of the definitions, so cells or pixels. Cells are used in more of an electrical context because that's what they use to collect the data. Pixels is what you're going to start seeing on your screen. And you put a whole bunch of pixels together to make an image, and like a whole grid of pixels. Then we have radiation. So radiation is from the sun. It is what's being emitted. It can also be what's being reflected. So radiation is referring to that energy levels that like transfer through the medium, which is our atmosphere. Then we have a sensor. So the sensor itself is what collects the energy and helps us create an image from that. Then we have the platform, which is the structure that the sensor is on. So we can have some in space, we can have some in the air, we can have some on the ground, we can have some that are just outside our body or on our body. So sensors are kind of all over the place. Sensors are all over the place, so we need to classify them as a platform. Then some of the words that you saw there, so scattering, again, just as a refresher, scattering means the light comes from a source as a beam, if you want to consider it a beam. But it comes down, it interacts with a target, and then the light or the energy goes everywhere and all over in different directions. And only part of it actually goes back to the sensor. There's absorption, which we'll talk about in great detail later. But absorption is when the energy kind of dissipates into a different kind of energy. So I can send light into the atmosphere. It can interact with particles and be transformed into long-wave radiation, which would be thermal energy. And so if we're following conservation of energy, that is exactly what happens. So using that rule that energy cannot be created or destroyed, it can only be modified. So that's where absorption, it doesn't just like disappear, it becomes in another type of energy for us. Then there's transmission. So transmission means that it is energy that goes through something. So it's usually a transparent medium, but we'll also have transmission through translucent mediums as well. It just means that the energy goes through it rather than getting stuck, like absorbed or scattered before it goes further on. The last one is acquisition. And so acquisition is the word I'm going to be using as we get data. So we're going to acquire data. The sensor acquires data. Everything is through acquisition. It's not necessarily getting, right? So I'm trying to improve that vocabulary as we go here. So the next objective is explaining the sources and radiation principles. So I have a few things here that we can talk about and a few slides on this. So the first thing that we need to talk about before we can really get into sources is talking about the electromagnetic spectrum. Now I know that it comes up later in the course outline, so we'll repeat that when we get there. But the electromagnetic spectrum is essential for us in remote sensing. So in my career, I've had to deal with, and I've seen and used images with gamma radiation all the way up to microwave radiation. Radio is really hard to make images with, but the rest of it I've worked with. So, for example, gamma rays are used in nuclear medicine. And so you can put in what's the word I'm looking for? I want to call it a contrast agent because that's the actual name, but I'm trying to find a simpler version for that. You insert the radioactive material into the person, and then you can use detectors that will actually show you where the majority of the gamma rays are being released based on that. And usually that happens at cancerous locations. So that's gamma radiation. X-rays, well, we all know looks at bones, and actually X-rays can look at other things such as CT scans. You can see some different kinds of tissue as well in CT scan, such as your brain. So again, X-rays are actually very interesting. They're quite fascinating to study. Ultraviolet radiation, we do use that because it helps us with atmospheric modeling, and it also gives us information about the atmosphere. But it's not part of our visible spectrum yet. Everything from ultraviolet, X-ray, and gamma ray are very high energy radiation. So therefore, they tend to be like, oh, don't get too much of it because it's going to cause cancer, right? Too much of anything will cause cancer. But that just gives you sort of that high energy. That's what's happening. And it tends to scatter faster. So the higher the energy, the faster it scatters. And we'll get into that later. Then we have visible light. So you can see visible light is a very small portion of the electromagnetic spectrum. That is what our eyes can see. So everywhere we look, that's what's part of it. Then we have infrared. So infrared is not just thermal infrared. Now this drives me kind of bonkers a little bit because a lot of people think infrared and they just use the general statement infrared for anything that heats up. So how many of you have been burned by your remote for your TV as you press the button and you point it at somebody? Probably none of you. How many of you have gone out and touched a tree and burnt your hand when it's like nice and green? Probably none of you. So it's very unlikely that you're going to like touch leaves, green leaves, and you're going to burn your hand. So the thermal energy of that is it's only just a small portion of the infrared spectrum. So you can see here, I've broken them up into, this particular reference, broke them up into different sections. Now I'm not worried about you remembering the wavelengths. Don't worry about that. But what I'm worried about is you knowing the names. So you can see right beside the visible light, we have near infrared. Right beside microwaves, which is over here, is far infrared. High-tech terms here. So near is always close to the visible light, far is closer to microwaves. Then we have shortwave infrared, we have midwave infrared, and we have longwave infrared. So you can see the thermal infrared kind of spreads that whole section. But for the most part, we deal with the thermal infrared in this section here. Short and mid are not always used, mid especially is not used all the time for thermal infrared. So thermal infrared is only a portion of the infrared spectrum. Near infrared is actually the highest reflection of near infrared is green vegetation. Shortwave infrared is soil. And so again, and that's just like dark black soil. So that's not thermal, it's just healthy soil that has very high shortwave. So, and then mid-infrared is when you start getting into elements. So you might be looking at salty soil or something like that. So that is the electromagnetic spectrum. There is an activity in class that we'll be doing, and so we'll work on that in class. But that is, this you need to know. You need to know the order. You need to know kind of what applications you might use them for. It's really important. Microwave, we're going to do a whole section on that later. That is my specialty. That's what I do. I've done everything from space to airborne to terrestrial, now to medical. So I love microwaves. They're super fascinating. They can do like a lot, almost as much as the infrared, right? So they do a ton of stuff. So they just have so much information in them when they come to a sensor. But we'll get to that later. But just to know that there's a huge bias on that part of the course because I love microwaves. So getting into kind of the next section of this, we have the atmospheric and terrain interactions. So this is where we're looking at sources. So there's two different kinds of sources. The first source is the sun. The second source is the sensor. So in this picture, we have what we call a passive sensor because it is coming from a separate source. So that separate source is often the sunshine. Or it could be, for example, a thermal. It's very rare that we're going to actually like send thermal energy to receive it back because it just doesn't work that way. Thermal is a little bit of a different beast. But for the most part, like infrareds and visible light, ultraviolet, even X-ray, a lot of those have a source from elsewhere before it comes to the sensor. The sensor doesn't send out X-rays, for example, I was actually quite intrigued by that. It's very fascinating stuff. Anyway, so going back to this, so we can see that we have our source, we have all these things that are happening that we talked about earlier. So we have absorption, scattering, transmission, more scattering. Then it comes down to the ground, we have more scattering, we have absorption, we have some being absorbed by the atmosphere, we have more scattering, We also have emission, which adds to the information that we're looking at, and then it goes to the sensor. So the sensor itself can be on different platforms. We'll get into that at a later date, but I've already mentioned them. And but the major thing is the source. So it does not have to be the sensor, but you can think of it as a sensor that has a flash on it. If it has a flash, therefore it has its own data, that is considered an active sensor. If it does not have a flash and you need to use a light in the room or you need to use the sun, it is considered a passive sensor. So then we need to know some basic wave physics. So here's two different kinds of waves. We have longitudinal waves and we have transverse waves. Longitudinal waves, that was one of the original ideas as to how light worked. There's a whole great history on it and it's really quite fascinating. But now we use the transverse waves as our theory of light. So again, there's several theories that are out there, but transverse wave is the one that we're going to use. So some of the important factors of it is that we have it starting, it follows through this nice like wiggly line like a snake, and it goes in this direction from, like for example, the TV to your eye. The amplitude is how bright it is, so we'll be getting into that when we get into talking about pixels. And then we have a wavelength, which goes from trough to trough or crest to crest. And everything we refer to is going to be in wavelengths in this class. Sorry. So then frequency is how often this happens over time. So the larger the wavelength, there's actually an inverse relationship. So the larger the wavelength, the smaller the frequency. And then reverse. So if the smaller the wavelength, the larger the frequency, back and forth. They're inversely proportional to each other. So that kind of concludes a little bit of the theory behind it, and just a little bit more of that background. So I'm going to stop the video here, and then we're going to move into objective 1.4 in the next video, just so you're not sitting here for a full hour and you can take a break.